Well, the earlier football means we're running about 10 minutes later than planned tonight on BBC One. But now a journey to Mars with Patrick Moore and the Sky at Night.
Good evening. For this programme, we're going to look for life on Mars. We're going to go there via the Antarctic. For the last part of last year, Mars was prominent in the evening sky, looking like a bright red star. It's less unlike the Earth than any other world we know. It's smaller than we are, further from the sun, and colder, but on the whole, not too unlike. And of course, it's always been regarded as the one world beyond Earth where we might find life. And here's a recent picture of Mars. You see there the polar ice cap, the dark markings, the red deserts, and the clouds. Because Mars does have an atmosphere, even though a very thin one. The first man who looked at Mars through a telescope was Galileo, way back in 1610. He saw no markings, but in 1877, Schiaparelli, the Italian astronomer, did. Using a very fine 9-inch telescope, he made drawings of Mars, and here are some. Again, the dark markings, and those streaky features he called canali. That means channels, of course, translated inevitably as canals. And what were they? Were they artificial? Schiaparelli had a totally open mind, others didn't. The American astronomer Percival Lowell built a big observatory at Flagstaff in Arizona, set up a magnificent telescope, there it is, and made drawings of Mars showing canals. And those are Lowell's drawings of Mars. He was quite sure they were artificial waterways. And he said that Mars is inhabited by beings of some kind or other is as certain as it is uncertain what those beings may be. Now, had those drawings been accurate, then Mars would have been inhabited. But sadly, they're not. I've used Lowell's telescope many times in my moon map days, and here's one of my drawings of Mars, made with that telescope, and no canals there. And some time ago, I decided I'd make a test. I took a modern map of Mars, based on the space probes, and on that, I superimposed Lowell's canal network, shown there in red lines. And there was absolutely no correlation at all, so sadly, those canals were purely tricks of the eye. And Mars is not suited to advanced life. Well, what about entirely alien life? My mother's impression, aren't they lovely? But I very much fear when we go to Mars, we are not going to go boating on a Martian canal, and I wish we could. Now, of course, we've learned a great deal. We've sent space probes there, and our knowledge of Mars has increased tremendously. There's Mars Global Surveyor. And on Mars, huge volcanoes. Here's Mount Olympus, the largest volcano in the solar system, a 300-mile base and 3 times the height of Everest, and a 40-mile caldera in the top. And there are things all that look like riverbeds. That looks so like an old, dry riverbed that I'm quite sure it is one. And now we have the new probe, Odyssey, going around Mars, studying the surface, and trying to find out the composition of the surface, where we might possibly find subsurface ice and even water. Of course, there are some people who believe there has been evidence of life on Mars. Some meteorites, found in the Antarctic, and here is one, are said to come from Mars and to show traces of past Martian life. I am highly skeptical, but one day we will find out. Now, on Earth, what's the nearest approach to life on Mars? I suppose the place less unlike Mars than any other is in Antarctica, the dry valleys there. Little water, freezing cold, and bitter winds. More Martian than anything else. Now, one person who knows more about Antarctica than anybody is probably Dr David Wynn-Williams of the British Antarctic Survey. Well, David, welcome to the Sky at Night.
Thank you.
Can you say a bit more about these fascinating dry valleys?
Certainly, the essence of the study of life is water. Chris McKay, who is a scientist at NASA Ames Research Center in the States, has a model for water on the surface of Mars. He believes that about 3.5 billion years ago there was a lot of water on the surface. There would have been rivers, lakes, possibly even a northern ocean. And then as moisture was lost from the atmosphere and got frozen into the permafrost, it would have retreated into ice-covered lakes. And we have these in the Antarctic, hypersaline lakes with a layer of ice on the surface and then clear water down to the bottom. But eventually even that water would have disappeared, and the only place we would have found moisture would have been inside rocks, as much as 8 millimeters inside sandstone, translucent sandstone. So you have a sequence of water which could produce potential habitats on the surface of Mars.
What about life there?
Well, the life would have changed with the water itself. There could well have been plenty when there was a lot of water in oceans and so on. It would have formed mats on the bottom of the lakes, and these would have been the sort of organisms like cyanobacteria, which are the old blue-green algae, and photosynthetic bacteria. The sunlight is readily available energy, and so they could have formed really quite dense mats on the bottom of these lakes because the ice and the water are so clear. We have these in the Antarctic, we know they exist, and there are parallels possibly on Mars. If you look around the edge of ponds, you find mats of cyanobacteria growing quite thickly, and you can see that they're often pigmented. This is partly to harness light and partly to protect against ultraviolet, which we'll come to later. If you look at them down a microscope, you'll see they're filaments which form a layer over the surface of the soil.
Spaghetti.
Spaghetti, absolutely, and these glow in the dark. We use an epifluorescence microscope to display them, and we can actually quantify them and use them to study the changing environment, like the effects of UVB in the ozone hole. So they're quite useful as well as being examples of the sort of microbes we'd find. Eventually, the sort of microbes you'd find inside rock would contain these cyanobacteria and perhaps algae, which are a bit more sophisticated. But in the Antarctic, we find layers of organisms inside the rock. The outermost layer of the rock would be a layer of black lichen, and then inside that you might have a layer of fungus, because a lichen is a combination of fungus and algae, and then the innermost layer, perhaps 8 millimeters in, would be algae and cyanobacteria. And if you look at the structure of the fabric, you can see they're actually within the crystal structure of the rock. And if you use a scanning electron microscope to magnify them tens of thousands of times, you can see they're embedded in a layer of mucilage, and they're actually attached to the crystals themselves. So these are the sort of microbes we might well find on the surface of Mars, living right at the limits of life.
What particular research are you doing at the moment?
We're particularly interested in the biomolecules that these organisms produce. So we're looking for the sort of compound that we could recognize by a remote mission. And the sort of things we're looking for are molecules which produce what we call a Raman spectrum. Now, the Raman phenomenon was discovered in 1928 by a Professor C.V. Raman, an Indian scientist.
Yeah, he is.
And he discovered that if you shine laser light into something, because all molecules are vibrating, whether organic or inorganic, they scatter the light, and some of the light comes back at a different wavelength from the original laser light. Now, I'm using a laser pointer here. If I shine this laser pointer onto the surface of some lichens which come from the Antarctic, this is an actual Antarctic rock, most of the laser light comes back at the same wavelength as on the original pointer. But some of that light will be scattered at a different wavelength according to the energy state of the biomolecules. So each compound, pure compound, will produce a unique Raman spectrum. And I have a couple of really quite well-known examples here. I have a carrot, which contains beta-carotene, everybody knows what these are, and a cabbage. And the carrot contains beta-carotene, which is a red pigment, and you can see the Raman spectrum for this beta-carotene, very distinctive. Chlorophyll is the green stuff in the cabbage, and that also produces a unique spectrum. And if you compare the two, you can see they're quite distinctive fingerprints. Now, these can be used to recognize these molecules without even knowing what their names are. We don't have to know it's chlorophyll, we don't have to know it's carotene. We also find beta-carotene in the Antarctic in microbes, and you can see if you look at red-colored snow, it contains snow algae. And the red stuff in snow algae is beta-carotene and other pigments. So we can actually shine the laser into these microbes and recognize the pigments that are characteristic of them. Now, if you do this sort of thing with a lichen like this one here, you can shine the laser in and you get the spectrum for carotene, and you can get the spectra for other ultraviolet screening pigments like parietin. And if you look at these Raman spectra here, you can see the beta-carotene and the parietin, separate fingerprints, and if you look at the combined spectrum for the whole lichen, you can recognize the individual peaks.
If there are organisms on Mars, what kind of pigments would you expect?
I would expect them to be driven by solar radiation. They would need two sorts of pigments. They would need pigments to harness solar radiation, chlorophyll and things like that, and they would need different pigments to protect themselves against ultraviolet damage, just like we do. Our skin goes brown in the sun to screen out the dangerous UV. And to recognize these, we use a miniature Raman spectrometer, the sort we can take into the field and hopefully take up to Mars one of these days. And this here is an example of miniature Raman spectrometer. This was developed by Montana State University as part of an international collaboration. And what we're looking at here is the microscope part at the end of a fiber optic cable, the orange cable, which goes into the spectrometer, which is the golden cylinder. And that in turn is attached to a camera. And the camera is connected to a computer, so eventually we can shine the laser into the microbes, whatever they are on Mars. It's a lichen here, but I'm not expecting surface lichens on Mars. But they might be inside the rocks. And we can then recognize these spectra without knowing what sort of compounds are present on Mars. We don't need to have any preconceived ideas. This has been developed as a collaboration between the British Antarctic Survey and Montana State University. And we too have our own cold deserts. And by a very happy coincidence, we work at a place called Mars Oasis, because our part of Alexander Island down the Antarctic Peninsula is surrounded by glaciers that have astronomical names. And the closest one is Mars, and that flows into the Saturn Glacier, for example. And so this site is where we will be testing this instrument next year. This one has only been put together in the last 10 days, and it's very difficult to get all the instrumentation to line up with 10 days' notice. It came from 4 different laboratories. This time next year, we will actually use it in the field, and this year we will bring samples back to test it in the laboratory.
Fascinating. Would you expect any resemblance between Antarctic life and what you might find on Mars?
Very much so, because the sort of microbes we've been talking about form layers in the bottom of lake beds. And on Mars we have craters like Gusev crater, which has a lot of evidence of fluvial forms. It has a river flowing into it, it has deltas, we can see sediments, we can see these layers. If we drop one of these miniature Raman spectrometers onto that sort of area, we'll be able to go down into the profile of the lake sediment and sooner or later go in through these different layers of microbes. We're going to try this sort of thing in the Antarctic at places like Lake Vanda, shown here, and the bottom of the lake has layers of microbes alternating with mineral material. So our logic is, if we can drop one of these into a crater where there has been a lot of water, like the Splosh craters, where you can see that it's not only minerals that are being displaced by a meteorite, but also water, then sooner or later we're going to go down through one of these horizontal strata of what we call stromatolites. We have examples of these stromatolites on Earth. We get them in the bottom of the Antarctic lakes. We also find them on the surface. We find them in places like Australia. Shark Bay, for example, shown here in a nice warm environment, has these layers of cyanobacteria alternating with mineral. So we know they exist on Earth. We find them in the Antarctic, which is the Martian analogue. And what we're particularly interested in is looking at the ancient Martian sediments. Now the challenge is that there was water on Mars back to perhaps 1.5 billion years ago, and the stromatolites on Earth go back in the fossil record to 3.5 billion years. But what we find very exciting is one of the chemicals produced by these cyanobacteria is called a hoponoid, and here we have a Raman spectrum of a real hoponoid 2.5 billion years old on Earth. So if we find these molecules that old on Earth, we might find them on Mars in the fossil record.
In the solar system, Mars is nearly in the right place, and not quite. We have the habitable zone round the Sun, Venus on the inside, a bit too hot, Earth nicely in the middle, and Mars on the outer edge, cold, but perhaps not impossibly so. But on Mars, what about the possibility of liquid water on the surface?
It's most unlikely to be pure water on the surface, but it's quite possible it's saline water. Lake Vanda, for example, is hypersaline, very high concentration of salt at the bottom. And the solar energy goes through the ice and through the water into the sediment and warms up that bottom water, which is plus 25 degrees Celsius because the salt concentration is so high. The water just can't rise by normal convection. So it's quite possible that hypersaline water is present in the profile of Mars, in the bottom of these lakes. And there is some imagery from NASA, from the Malin and Edgett papers, showing possibly relatively recent rivers or at least some sort of channels of water flowing perhaps 10,000 years old, as recent as that, very recent geologically. But that could well have been saline water at minus 50 degrees Celsius, because it doesn't freeze till then.
In spite of the low atmospheric pressure, below 10 millibars.
Absolutely right. Bob Haberley, again at NASA Ames, has a model which indicates you could just about have liquid water in certain parts of Mars, allowing for this water pressure. But it's all to do with the triple point between liquid water, vapour and solid. But it is conceivable, and his model didn't even include the saline angle. So it's quite possible the biomolecules we've been talking about could have been flushed out of the profile by this flow of salt water.
That's encouraging. Well, now, David, for the $64,000 question. All in all, do you believe there is any trace of life on Mars?
I think personally there was life on Mars, and our objective is to find biomolecules that indicate the presence of former microbial activity driven by solar radiation. But that's not going to be right on the surface now because it's a cold desert and fried by ultraviolet. But there may well be life deep in Mars, perhaps a couple of kilometers down, driven in a deep dark biosphere by chemical reactions. But we're not going to get down to that in the near future.
When do you think we'll know definitely?
Well, I would think they would do deep drilling programs in perhaps 10 years' time, but it would need possibly men, geologists, to get up there to actually do some experimental research of their own to guarantee success with that sort of research.
One thing does strike me, you know. If we find any trace of life on Mars, either past or present, it'll surely indicate that life is probably widespread in the universe.
I would certainly agree with that, and it could well have come in our direction as well, because we might one of these days find a Mars meteorite with microbes in, but we haven't found one yet.
No. Well, what about the possibility of manned flight to Mars?
Well, I think it's certainly on the cards. NASA is talking about future missions. There is certainly a lot of enthusiasm for that, and we are a planet of explorers. So I think it will be one of these days we will have a Mars mission up there with a geologist, with perhaps a Raman spectrometer in a rucksack on his back, and he might be able to recognize these molecules for himself.
Well, looking far ahead, I wonder what a Mars base is going to be like. Well, here's a Tony Wilmot impression of a base on Mars, and I just wonder when that will come about. 10, 20, 30 years? What's your guess?
I would guess perhaps 15, 20 years, and that picture reminds me very much of one of our Antarctic bases, so we're learning from personal experience.
Well, we're learning so much more about Mars now. More probes are going up, and I'm quite sure the next year and the next few years are going to be very, very exciting indeed. And I think Mars still has many surprises in store for us. David, thank you very much.
It's a pleasure.
Don't forget, it's newsletter time. Want your newsletter? Send your Stanford envelope to Newsletter 84, The Sky at Night, BBC TV, London W127TS. You can consult our website, www.bbc.co.uk/space, and for the observational notes, CFAX page 620. And so, next month, a very happy New Year to you all, and for now, good night.